All right, good evening, guys. Welcome to another evening. Today we're going to continue on vectors and to see how far we can get with vectors today. Hopefully, if we are able to, we'll try to wrap up this topic at the end of this class. If not, then we will continue this class on Sunday. All right, guys? All right, so recall I had defined what a vector is. A vector is a quantity that has magnitude and direction. And when we talk about magnitude, we're talking about the size of the measurement. When we're talking about direction, we're talking about exactly what direction the vector is going in relation to either east, west, north, or south, or in relation to angles such as bearings or so on. All right, so we also talk about scalar quantities. So quantities that don't, that only have magnitude but no direction or don't rely on direction. Those are scalar quantities. An example would be time, temperature, length, and so on, mass. Example of vector quantities would be force, velocity, acceleration, displacement, etc. All right, and so today we are going to be picking up from parallel vectors. We say that two vectors are parallel if they have the same direction. So they don't necessarily have to have the same magnitude. And remember, we use a line segment to represent a vector and the length of the line segment to represent the size of the vector. And so we will have the length in a scale. And if we are whatever unit of measurement that vector is in, we will take a scale length to be that unit. For instance, if we are measuring force, the unit for force is Newton. And so we would make a scale like say 1 centimeter represent 1 Newton. So if the length of the line is 3 centimeters, then you know that that line would represent a magnitude of 3 Newtons. All right, guys. So parallel vectors have the same direction, but not necessarily the same magnitude. And when you have one vector being larger than another one by some amount, we say that the amount that it is larger by is based on the scale factor K. K is a multiplier of the smaller vector. And when you multiply the smaller vector by K, you will get the length of the larger vector. In this case, A is the larger vector, B is the smaller one. So we can say the length of A is equal to K times B, right? So A is equal to KB. So it means that if you multiply the length of B by some amount, you can get the length of A. All right, everybody is clear on that? Any question? Now, if two vectors are going in opposite direction, so in this case, we will talk about the vectors being antiparallel. And just like parallel vectors, their magnitude won't necessarily be of the same size. All right. All right, so with that said, let us move on. And here we have some vectors, and we can compare them in terms of whether or not they're parallel. So based on what you're seeing here on the diagram, what are the vectors that are parallel here? What are the parallel vectors? I think I probably have to ask somebody in particular, Miss Caveira, which of these vectors would be parallel to the vector A?
It would be 3/2.
Okay. 3/2A. What else? Anything else?
I don't know if -2 would then be 1, even though, but no, it would have been 1.
Well, we don't really have a
2 and 2A could be parallel to.
2A would be parallel. All right. What else?
Half A.
Half A. All right. So those are parallel because they're going in the same direction. What about -3A and -A? What would you say about those? In relation,
They're going in opposite direction.
in relation to A. So what would you call those? When vectors are opposite,
They're
antiparallel.
They're antiparallel. Good. What about the one with the question sign? Is that parallel or antiparallel?
Neither.
Right. So that one would not be neither parallel or antiparallel. All right. So you get the idea of what we mean by parallel and antiparallel. Now, in terms of the parallel vectors, tell me the scale factors that you identify. All right, let me ask Ms. Green to do that. What are the scale factors of the parallel vectors, Ms. Green? What would be the value of K for the parallel vectors? Are you hearing me, Ms. Green? Are you there? Respond, please. Ms. Green, are you hearing? All right, Ms. Green is not responding. I'm not sure why. Ms. Doherty, what would be K for the parallel vectors?
Sorry, like 3/2.
Right, so 3
of 2A and 3A.
Which of these scale factor would represent an enlargement of the length of the vector? Remember, we are comparing these vectors to the vector A. Which of these scale factor would be a larger vector than A?
2A?
No.
2A, yes, 2A would be one. Which other one?
And 3/2, sir.
3/2A, right? Is there any more? All right, so if we are referring to -3A in terms of magnitude, it would be larger. But in terms of whether or not it's parallel, it would not be parallel. It would be antiparallel. All right. Now, what you notice about the scale factors that give you the larger vectors than A? What is the range of value for K? Remember, when you're looking at the scale factor, we say that if K is greater than 1, they will magnify or give an enlargement of the vector. Same thing for if you're in an image. If K is a number greater than 1, So in this case, 2/3 is greater than 1, 2 is greater than 1. You multiply A by these values, you get a larger vector than A. All right. Now for the scale factor 1/2, you notice that this vector is smaller than A because instead of this scale factor making a larger vector, it is making a smaller vector than A. So this would be a reduction in terms of A. Is that clear, guys? Raise your hand. Miss Green, are you there? Are you following?
Yes, sir, I'm here.
Oh, were you there all along?
No, sir, I went somewhere for a second.
Okay, calling on you just now and you weren't responding. All right, so moving on. So you get the whole idea of what a parallel and an antiparallel vectors are. All right, so inverse vectors. Now, we say equal and opposite vectors. So if two vectors are the same magnitude, but opposite in direction, they are inverse to each other. A minus sign is used to denote the opposite direction. All right, now, so if you're going one way, and if you're in this case, if you know about follow the arrow, you ever hear this party thing that they usually have named follow the arrow? Anybody know of that? Well, if you follow the arrow, that means you go in the direction where the point of the arrow is going. Then you notice that these two vectors, one is going from A to B, and the other one is going from B to A. That means they are inverse of each other. Not why they are inverse of each other, not only because they have opposite direction, but because they have the same magnitude. So same magnitude and opposite direction, they are opposite to each other. Now, one of the things I want you to think of in terms of inverse vectors, I want you to think of them in terms of positive and negative of the same number, right? So let's say that the length of A was, say, from A to B. Let's say that the length of that line was, say, call it, say, A. If this is A, this vector coming back in the opposite direction from B to A would be minus A, all right? And in a similar way, if these vectors are given actual values, then you're going to treat them in the same way. So let's say that this one from A to B was, say, 3, then from B to A would be minus 3. Do you get the idea, guys? Is that clear? That if they have the same magnitude and opposite direction, one is negative to the other with the same value. Guys, read that. All right. So in that regards, when you're adding vectors, which we'll be looking at shortly from now, when you're adding vectors, if you're adding a positive and a negative of the same vector, then clearly you need to, what would you need to do? You need to subtract. So when you subtract, you would have 0. So here we have from A to B is the same as the negative of B to A. Is that clear, guys? Now notice the negative of AB. You flip around the numbers, the letters, and then you put a minus sign. So if you follow the arrow, you're going from A to B. The negative will come back from B to A, right? So just be clear on that, guys. All right, moving along. So in other words, when you add these two vectors, your resultant would be 0. And I'll define what resultant means for you in terms of vectors. All right, so moving on. Next, here we have an example here. It says C is the midpoint of AD, which is that length of line going from A to D. And they say AC is equal to A. C is the midpoint of AD. This C here should be a capital C. This is supposed to be a capital C, this C here, all right? So that's a midpoint. So we are saying from A to D would be the entire length, and from A to C would be halfway in between A and D, all right? Now the length of AC is labeled common A, right? So we are treating the length here with unknown values. So we are actually doing a kind of algebra here. So if the length of AC is A, then if C is the midpoint, that means the length of CD from C to D going to also be the same length as A to C. Do you agree? Do you agree, guys? Miss Green, do you agree? Miss Green, are you there?
Second over, please.
So I was saying that given that we have this line from A to D, right? And they tell her that C is the midpoint. They tell her that the length of AC is common A. So I am saying that the length of CD must also be common A too. Do you agree?
Think so.
Say that again, Miss Green. What would make the...
I think so, sir.
Huh? Say that.
Sir said, I think so. I'm not really sure.
Okay. All right. Remember when we talk about equal vectors, what are equal vectors? Vectors that have the same length and same direction, right? Now, if you have A to D and you cut it in two equal parts and the middle is C, that means they would have the same length. Do you agree with that? Ms. Green? Let's say that this was a card, Ms. Green, and you double it, you fold it in two halves, in two parts. Wouldn't you say that from A to C and C to D would be the same length?
Yes, sir.
Right. And since C, you're going from C to D, that means the arrow would be pointing from C to D. And it means that these two lines, they are on the same straight line. And the arrows are pointing in the same direction. So it means that the two vectors have the same direction and they have the same magnitude. So in that regard, we can say CD is the same as A, meaning that it is equal to the same magnitude and direction of AC. All right, so if CD is A, then we can say that the length from A to D would be equal to AC, the length of AC plus the length of CD. So we know that AC is A and CD is also A. So the entire length of AD will be 2A. You following that so far? Miss Cabrera, do you follow that? Respond again, Miss Cabrera.
Yes, sir.
Okay, Miss Darty, are you following so far?
Yes, sir.
All right, now if you go back to the question, what did the question ask you to do? The question says you have to express the vector dA in terms of A. Now, when you look at this line up here and you think about dA, you notice that dA would be going in the opposite direction of AD. Do you agree with that?
Yes, sir.
Right, so if it is, so we know that AD has a length of 2A. So we say since DA is the inverse of AD, then DA must be minus 2A. Everybody follow that? Miss Green?
Yes, sir.
Right. So in terms of A, dA would be equal to minus 2A. And this is the kind of reasoning that you're expected to show when you're working with vectors, all right? It seems a little tricky, but it is really not. You just need to look at what the different vectors that you're adding together and relate them based on their direction, all right? We'll see how to do some more of these. All right, so don't worry about it. All right, so here now we are going to be talking about resultant vectors. Now, resultant vectors is really what we refer to, the result that you get when you add component vectors. Now, component vectors would be the sum of more than one vectors. When you sum up more than one vectors, the overall result that you would get would be equal to a single vector that we call a resultant vector. So what is a resultant vector then? So a single vector that can take the place of two or more component vectors is called a resultant vector. Now, when you look at this diagram here, the resultant vector is this single vector that goes from A to C. This is the resultant vector. Now, the other vectors that are summed up together would be the vector A to B and then B to C. So these are two other vectors that we sum up together. But what you notice about these component vectors is that the arrows on the component vectors, they are actually going from head to tail. So the head of the nose of this arrow here is going into the tail of this arrow here. And when component vectors are followed in that way, you will notice that the resultant vector would be a straight line starting at where the component starts and ends where the component ends. So when you have a group of component vectors that are starting off at a point and they are following nose to tail, now the single vector that can start at the same point and ends at the same point of the components is known as the resultant vector. So this single vector would be the resultant vector AC. And what we are saying about AC being the resultant vector, we are saying that the vector AC could have gone straight to the point C without going through A to B and then B to C. Now, the tricky part about vector is that we tend to add vectors and treat them as though we're adding numbers, but vectors are not really added in the same way as how we add numbers, right? Because the arithmetic method of adding numbers is that we would add the arithmetic values, but since vectors are not actual just values, but they are lines, then we have to consider the length of the line when we're adding vectors. All right, so we'll see more of that as we go along. So this is saying, considering the following, to get to the point C, we move from A to B, then from B to C. Or we could move from A directly to C. Now, this would give us the vector AC. So AC is equal to the vector AB plus BC. So AC here would be the resultant vector. And we are saying that if you add the component vector, these are called component vectors. If you add them together, you will get the same result as the resultant vector. Now, so if the length of A is common A, if the length of AB is common A, length of BC is common B, then the resultant vector AC is going to be the sum of A plus B. Now, I'm using the word sum loosely, and I'm using the word equal loosely. Now, equal does not mean equal as in arithmetic, and plus does not mean plus as in arithmetic. They have totally different meaning when we are dealing with vectors. So I'm going to explain the meaning of these, all right? All right, here we say that AB together with BC is equivalent to AC. Now, so what this is telling you, the plus sign, we read it as together with, right? So in vector, when you see the plus sign, you are saying this vector together with this vector. The equal sign means equivalent to, all right? So how to read vector, you're saying that the vector AB together with the vector BC is equivalent to the vector AC. So when you think of it in that way, you know that you're really not adding in the same way as arithmetic, and you're really not using the equal sign as the same way in arithmetic. So just bear in mind what these symbols mean when you're using them in vectors. Is that clear, guys? Raise your hand. All right, so now when we are looking at the, you may lower your hand, guys. When we are looking at the component vectors, you must always look at the arrow. So the nose of one vector, the nose of one arrow, or the point of one arrow must be going into the tail of the other arrow. If they're following nose to tail, it means that any vectors that are following nose to tail, within that direction, that vector will hold the same sign. They are going in the same nose to tail. So if they are positive, they will be, the two vectors will be positive. Now, one vector can be going in the opposite direction. So you'll find that the nose coming opposite. So you find if you have a nose to nose, meaning the point of one arrow pointing in the opposite direction, then you know that one going to be negative and one going to be positive. All right, so that is the key thing about component vectors. And we'll see how to treat with those when we're looking at some examples. All right, any question, guys? Is it clear what I've just explained to you about the vectors? Guys, raise your hand if what I've just explained is clear to you. If it is not clear to you, just let me know so that I can see if I can